acidification is an increasing issue that is altering marine ecosystems as we speak. This process occurs when carbon dioxide in the atmosphere dissolves into the ocean water. The CO2 reacts with water to form carbonic acid, which increases hydrogen ion concentrations and lowers the pH, making the ocean more acidic. Ocean acidification reduces the availability of carbonate ions, a key building block for marine organisms like corals, shellfish, and plankton. Now, did you know that this isn't the first time Earth's oceans have faced this challenge? Today we explored the Paleocene Eocene Thermal Maximum and addressed the question, how do the ocean acidification events of the PETM compare to the ocean acidification seen in the present day? The Paleocene Eocene Thermal Maximum was a global warming event that occurred roughly 56 million years ago and lasted 170,000 years. The causes of the PETM are still debated, but two key factors most likely triggered this rapid warming and ocean acidification: massive volcanic activity from the North Atlantic igneous province and the release of methane gas from seafloor sediments. These processes released enormous amounts of carbon dioxide and methane into the atmosphere. Scientists estimate that around 3,000 to 9,000 petagrams of carbon were emitted, leading to a 60% increase in ocean acidity over thousands of years. Understanding ocean acidification during the Paleocene-Eocene thermal maximum comes from analyzing sediments and fossils from the time. For measuring pH specifically, one key method involves studying boron isotopes and boron-calcium ratios in fossilized plankton like foraminifera. These chemical markers allow scientists to estimate past ocean pH levels with more accuracy. Deep ocean species were heavily impacted, with 37% of benthic foraminifera being wiped out by the effects of the PETM. The ocean's carbonate compensation depth, or CCD, rose drastically, causing widespread dissolution of marine organisms with calcium carbonate shells or exoskeletons. While surface waters showed some resilience, deep sea ecosystems faced catastrophic consequences. It took tens of thousands of years for the oceans to recover. Let's fast forward to today. Since the Industrial Revolution, atmospheric carbon dioxide levels have increased by 40%, and ocean pH has dropped from about 8.2 to 8.1, which is roughly a 25% increase in acidity. Keep in mind that the pH scale is logarithmic. It should also be kept in mind that pH varies by geographical location and by ocean depth. This map displays a global distribution of surface ocean pH. Generally, lower pH measurements are found in the seawater near the equator. As a reminder, a lower pH indicates higher acidity. For more recent data, a variety of studies look at ocean acidification changes over the last few decades. This graph specifically, done by the EPA, looks at ocean carbon dioxide levels and acidity from 1983 to 2015. As you can see, they were comparing 3 different locations: Bermuda, Canary Islands, and Hawaii, and found significant decreases in pH, or increase in ocean acidity, over just the span of 32 years. Unlike the PETM, the rate of acidification today is at least 10 times faster, driven by human activities like the burning of fossil fuels. If current emissions continue, ocean acidity could increase 120% by the year 2100, a change that would drastically alter marine ecosystems. The lives of marine species would be threatened. The access of food, income, cultural practices, and more from people across the world would be significantly impacted. Recent studies have given us a glance into what we may expect for certain marine organisms. In one study done by a team at the NOAA, An Antarctic pteropod was placed into seawater, simulating the pH and carbonate levels that have been projected for 2100. As seen in the images, significant cell dissolution was observed over the course of 45 days. Without action, the future could mirror the devastation of the Paleocene Eocene Thermal Maximum, or more likely at current rates, become far worse. But through major efforts of mitigation, primarily a decrease in CO2 emissions, there may be hope. Reducing fossil fuel use, adopting renewable energy, and protecting marine ecosystems can slow ocean acidification. Individual choices matter, but systemic change is critical. Governments and corporations must take action. The PETM teaches us that the ocean's recovery is slow, but its damage can be swift. So let's work together to prevent history from repeating itself at an even greater cost.